there are many dating methods.
I'm single, tell me all about it.
That I won't talk about. However, there are some that I will. So what is a dating method in this context? No, you're not. A dating method is a way of estimating the age of something old, because evolution says this thing is 1 million years old. This thing is 65 million years old. This thing is 2 billion years old. So it's a way of estimating. And there are several kinds. There's radiocarbon or carbon-14, carbon dating. That's for organic material, plants, animals. And then potassium argon, uranium lead, rubidium strontium, and a whole bunch of other ones. All of them use radioactive decay, because there is a variety of radioactive materials, and they decay at a certain rate. And as they decay, you can notice things about them. So every radioactive substance decays over time. The time it takes for half of any amount to decay is called its half-life. So if you start with some sample size, one half-life later, half of it is there. Another half-life later, only a quarter of the original, because half of a half. And 3 half-lives later, only an eighth is left, and etc. So it goes down pretty quickly. And the half-life varies from one radioactive substance to the next. Radioactive decay is assumed to be statistically well-behaved and therefore useful for age dating, for estimating the age. So there's, like I showed a couple slides ago, there are quite a few different ways of doing radiometric dating, radioactive measurement dating. But we'll talk about carbon-14 because that seems to get a lot of press. Let's look into it. So how does it work? Carbon-14 dating, how does it work? Atmospheric nitrogen, 80% of our nitrogen, 80% of our atmosphere is nitrogen. So cosmic rays are coming in. That means high energy particles are coming in from the sun, from the stars, and these particles come in and hit the nitrogen-14, and turn it into radioactive carbon, or carbon-14. Carbon-14 is radioactive, which means it decays. Carbon-14, even though it's radioactive, its only difference is its nuclear attributes, not its chemical attributes, which means it can still combine with things like oxygen to make carbon dioxide, but it's radioactive carbon dioxide. Well, what happens to carbon dioxide? Well, plants bring it in. So carbon dioxide, or carbon-14, is constantly decaying back into nitrogen-14, but because the cosmic rays that keep coming in, the atmospheric ratio is about 1 in a trillion are carbon-14. All the rest of them are carbon-12, the usual, that's the normal, non-radioactive kind. So in the atmosphere, even though it decays, it's always being replenished by the cosmic rays doing their things on the nitrogen. Plants take up the carbon dioxide, whether it's radioactive or not, whether it's radiocarbon-14 or regular carbon-12, plants take it up, and therefore the plants also have 1 in a trillion of carbon-14. Animals and humans eat the plants. Therefore, animals and humans also have about 1 in a trillion carbon-14s. So out of every trillion carbon atoms in your body, about 1 of them is carbon-14. All the rest are carbon-12. As the plants and the animals or humans die, they stop taking in new carbon dioxide, carbon-14, because they stopped breathing and they stopped eating. So new carbon dioxide does not come into their bodies anymore, but the stuff that was already there decays. Okay, So if that is well behaved, then you can do some predictions from it. Comparing normal levels of carbon-14, like 1 in a trillion, to the levels in the dead things allows us to estimate how long ago they died because of the half-life. So here's what it looks like. Radioactive decay on the left is, here's 100% of your sample size at time 0. 1 half-life later, you have half of it left. 2 half-lives after you start, you have a quarter left. 3 half-lives later, you have an eighth left. And look at that table over on the right. 10 half-lives later, you only have 1/10% of your sample size left. 100 half-lives later, you have about a billionth of a billionth of a billionth of a percent left. But the carbon-14 half-life is 5,730 years. That's not very long if you're thinking about evolutionary deep time. So how many, okay, you're going to run into problems here because radiometric dating methods, they don't measure age directly. They just count atoms of a certain type. And then the number of atoms you find is plugged into a formula, into a mathematical model, but the mathematical models have unverifiable assumptions that are also there. You have one number that you can measure and a half a dozen other ones that you can't, and therefore you plug that one number that you can measure into there, guess on the other ones, and come up with a date. Well, what could go wrong? So there's a big caveat here. All dating methods rely on assumptions that we cannot be sure of. So this is something that Matthew alluded to earlier, the bathtub illustration. Suppose you arrive home and you hear water running. You trace the sound to the bathtub, which is filling at 1 gallon per minute. You know that the bathtub holds 45 gallons. The bathtub is 2/3 full. How long has the water been running? Any ideas? 30 minutes. Any other answers? Oh. So most people say 30 minutes, but is that right? Well, it's a yes, exactly. If you assume certain things, then that could be a right answer. 30 minutes is right only if certain assumptions are valid. For example, the tub was completely empty when you started. No one added bucketfuls of water by hand. No one removed any water. The drain was not open for part of the time. And the water's been coming in at the same rate the whole time. If you know all of the answers to those assumptions, and if all of those assumptions are correct, then it was 30 minutes. But all the dating methods have unknowns like this. We don't know if the bathtub was empty when it started. We don't know if it's been coming in at a constant rate. We don't know if some other process added or removed any, and we don't know if there was a constant, this like the drain example, a constant decrease caused by some other process that we don't know about. So let's just add some stuff. Let's just guess and get an answer. Yes, that's true. There are more assumptions. So here's a really important point. Radiometric dating methods are only as good as the underlying assumptions. That's a really important point. And a really important problem is we don't know if the assumptions are valid. Therefore, in fact, there's a lot of evidence that they're not. So, I'll ask that in a minute. Okay, so here are some examples of radiocarbon dating. So they've dug up coal, done some radiocarbon dating on it, and they say it's 20 million years old and it has detectable carbon-14. Fossilized dinosaur bones. They claim they're 65 million years old, but they still have carbon-14. Diamonds are 1 to 3 billion years old, supposedly, and they still have detectable carbon-14. So what's wrong with this picture? How many atoms are there in the whole world, in the whole Earth? Anybody have a guess? It's about 10 to the 50th. Okay, so how many times can you divide 10 to the 50th in half before you get down to 1? About 168 times. Now that doesn't take fancy math. You can just keep hitting the button until you get to 1 and count how many times you hit the button. But here's the fascinating part. Remember, the half-life of radioactive carbon is 5,730 years, which is not that long if you're trying to calculate ages, especially if you have a deep time assumption. A lump of carbon-14 as big as the whole Earth would be entirely decayed in less than 1 million years. I'm pretty sure those scientists who were checking the coal and the dinosaur bones and the diamonds were using a sample size smaller than the Earth. But a lump of carbon-14 as big as the whole planet would be gone in less than 1 million years. 168 half-lives of 5,730 years. So it is absolutely preposterous that you could say this thing is 20 million years old if it has any carbon-14 in it at all, or 65 million, or 1 to 3 billion. I mean, it's just astonishing that is still stated with a straight face. Since dating methods rely on assumptions, the assumptions are tuned to give the right answers, the desired answers. So let's see, if we plug this in, ooh, that says it's too young, so let's tweak this one. Not enough, let's tweak this one again. There, I like that answer. So if we make the assumptions just right, we can get whatever age we want. So measured ages that reflect what the scientists want them to reflect are accepted. When they do tests and they get an answer they don't like, they just ignore it or say it was compromised, it was diluted, it was corrupted, the sample size was something went wrong with the process or the sample, because we can't have an answer that young, because we all know deep time is a real thing. So radiocarbon dating of dinosaur bones gives ages in thousands, not tens of millions of years. But a research paper that described this was silently removed from public view. We can't have that. So, evolution actually is a religion. Listen to some of these quotes. Evolutionist Sir Arthur Keith stated, "Evolution is unproved and unprovable. We believe it only because the only alternative is special creation, and that is unthinkable." I want to believe this because I don't want to believe that. Where's the science in that? Kansas State University evolutionist Dr. Scott Todd, even if all the data point to an intelligent designer, such a hypothesis is excluded from science because it is not naturalistic. I don't care what the evidence says, I'm not going to believe it. That is a religion. That is not science. And Richard Longmont, materialism is absolute, for we cannot allow a divine foot in the door. Think about that. This is not science at all. These quotes are glaring examples of my mind is made up, don't confuse me with facts. Okay, so let's look at some rocks. Potassium argon is another radiometric dating method, and is it accurate? This one, potassium decays into argon, and they measure the number of atoms of this and the number of atoms of that and compare the ratios and stuff. And let's look at some examples. In Kilauea basalt in Hawaii, the actual date, according to eyewitnesses during this eruption, It happened in 1800, so it's about 200 years old. When they measured it with potassium argon, it says it was 21 million years old. It's 105,000 times too big of an answer. Is that a problem?
Rounding.
Yeah. Rounding, yes. The Hualalai basalt in Hawaii was 1801. How do we know? Because we have eyewitnesses. There were people watching it. 1801, and that sample measured 22.8 million years old. 103,000 times off. Kilauea Iki basalt, 1959. So, it's like half a century old, and it measured 350,000 years old. 139,000 times too big of an answer. Mount Stromboli, a bomb is a lump of magma that flies out of a volcano. It happened in 1963. It was measured at 2.4 million years old. Mount Etna basalt happened in 1964. We have pictures of it, and was measured at 700,000 years old. Mount St. Helens, 1980. It measured 2.8 million years old. 70,000 times too large of an answer. Okay, so we have eyewitnesses watching these volcanoes happen, and the rocks that come out of them are measured in the hundreds of thousands or the millions or the tens of millions of years. Why is that? Because of the assumptions. In the dating methods, we don't know this, so let's invent an answer and stick it in the formula. We don't know that one either, so let's put another answer in there. And based on the assumptions, we get those answers. So, New Zealand, Mount Ngaruhoe, has erupted several times since 1949. Samples were potassium argon tested in 2000. So these samples, 270,000 years old, 800,000, 1 million years, 1.5, 3.5 million years old, that's in 1949, and all of these, not in 49, but since 1949. All of these were less than 51 years old, because there were eyewitnesses that saw the volcano happening and picked up rocks from it. So here's a really good question. If ages determined by radiometric dating are demonstrably and hugely inaccurate for samples whose ages we do know, why should we consider them accurate for samples whose ages we don't know? The answer is we shouldn't. So radiometric dating, can it be used? Yes, but with the great big caveats of we have all these assumptions that we don't know, and therefore the answer might be unreliable. And if you look at the track record, there are a lot of unreliable. And that's that. Matthew, do you want to say anything before next piece? That's a good point. Any questions about dating methods or evolution itself?
I have a question, Dave.
Okay.
I took a picture. So let's see. That one, the doghouse. That one. The carbon dating question. I didn't quite understand. Maybe I just misunderstood what you wrote. The first one, carbon dating or carbon-14 dating. Atmospheric nitrogen, 14 nitrogen, is struck by cosmic rays and turned into radioactive carbon. So carbon and nitrogen are both elements, so how could one be changed to the other? I didn't quite understand. Maybe I missed what you were saying.
The atomic number, which is, there's an atomic weight and an atomic number. When the cosmic rays, these charged particles come in, it adds something to the, changes something in the nucleus. It doesn't change the number of electrons going around, but it changes the number of things in the...
The weight of the atom itself.
Yes.
Into another element.
Yes.
Okay.
So one of the neutrons is changed into a proton, which changes the element, but the weight remains the same. But that is a little bit unstable, so that decays back after a while. Yes?
If carbon-14, nothing can be older than 5,730 years old if it has any carbon-14 in it.
No, no, no. Half-life. So two half-lives is about 10,000 years. There's 1/4 of the sample size. 3 half-lives, 3 times 5730, there's 1/8 of it left. So yeah, it goes down, 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 but it takes quite a while to get down to 0. And the sample size determines how long it takes. So that's why it was very significant that a sample size the size of the whole Earth would be gone in less than 1 million years, because that's about 168 half-lives later. Yes, Bob?
I was just thinking, even a dead body has nitrogen in it. So, I mean, couldn't that throw the results off? The cosmic rays hit nitrogen in a dead plant?
No, because that happens in the upper atmosphere. Cosmic rays don't get down here because of the atmosphere itself, ozone layer. It ran into something already up there, so it doesn't get down here. So the carbon-14 is made high in the atmosphere, and then the atmosphere circulates, so that's how it gets down here. It's made up there, it just circulates to be down here, then plants absorb it, people and animals eat it. Carbon-14 is radioactive. Yes, nitrogen-14 is not. Yes. Correct. Yes, you're not measuring the nitrogen anyway. You're measuring the carbon-14.
And if there's no cosmic rays that can get down to the body or whatever it is, then none of the N14 could be converted to C14.
Correct. It will not, the nitrogen will not be turned into carbon down here because the cosmic rays can't reach that far because they run into stuff way higher. Right, and yes, and that's why the magnetic field of the Earth is so useful, because that deflects a lot of them. Some of them get through and make the carbon-14, but a lot of them don't, because God put a magnetic field around the Earth to protect it.
Do you think some of that drives the whole global warming, don't ruin the atmosphere, craziness out there? Is there afraid of the breakdown of that, allowing rays in?
Oh, well, if that is caused by the decay of the magnetic field, I don't think we can affect that in any way. I mean, even though the magnetic field of the Earth and every other planetary body that has it is decaying, there's nothing we can do about that. So eventually, yes, there will be a problem, but we will all be gone long before then.
Is it correct to say that with a, like you said, 1 part per trillion, right? With
Mhm.
14. So wouldn't that, one of the assumptions maybe then would have to be a consistent makeup of the atmosphere?
Yes, that's one of the assumptions that we don't know. Yeah, that is based on the uniformitarianism, because this is what we see now. We can safely assume that it's always been that way. Well, no, we can't. So, but that is one of the assumptions that they plug in.
And with rocks, do they try to say that the amount of time that it's been in the Earth's core affects that? Maybe?
No, since it was molten. For example, that's why they used lava coming out of volcanoes, because as the theory is that when the rock is molten, then argon, potassium argon, it can leave because the rock is still liquid. When it hardens, it locks it in. And, you know, that's an assumption too. There are 2 assumptions there. One is that all of it has left by the time it hardens, and that the other one is that it can't go out after it hardens. And yeah, stuff like that. So there's quite a few assumptions in there, and if we assume them, we can get an answer. And if we don't like the answer, just make different assumptions because, isn't that what you do?